Now, a question that may have come up that you have had is, we said that Newton developed this law of universal gravitation, but he didn't actually get the value of G. So the value of big G only came about 71 years after Newton's death. So we might ask ourselves, okay, well, if Newton didn't get the value of G, who did, and how did they actually get this? So it's a good question, and we're going to talk about that just for a moment here. So this experiment to find G, it was developed by this British gentleman named Henry Cavendish, and he performed this experiment called, go figure, the Cavendish Experiment. So he actually found the experimental value of big G, but that was just more of a, I won't call it an accident, it's just that was a byproduct of his original experiment. He had wanted to determine the density of Earth, but in order to do that, he actually had to figure out what this value of big G was. So Cavendish used this thing called a torsion balance. Now there's a lot of fine details to it, but I'm just going to go through it real quick here. So in this torsion balance setup, or this setup that Cavendish had made, Cavendish was pretty rich, so he could afford to build some really nice contraptions. So we had this kind of wooden frame here, and it was basically sealed off with the exception of kind of these openings here that allowed telescopes to be hooked up, and this was to observe very fine movements. So we're going to notice that we have some wires being suspended from the ceiling. So we're going to notice that directly attached to the ceiling here, we have these two gigantic lead balls that are hanging from that suspension. So in Cavendish's experiment, each of these lead balls, they're about 12 inches in diameter, I believe, or I think they're 12 inches in diameter, and they each had a mass of 158 kilograms. Now, compared to that, we also had these really small lead balls here, and these were less than a kilogram in size. And you'll notice that these even tinier lead balls, they're hooked up to a separate suspension system. What Cavendish was trying to do is he was trying to look how much this wire that was attached to these two smaller lead balls, how much it kind of twisted in the presence of these two larger balls. Because if we kind of follow the suspension of those two smaller lead balls, you'll notice that this leads to a fiber that's leading up to this thing called the suspension head. What Cavendish did is when those tiny balls moved in the presence of the larger lead balls, what he noticed is that this fiber would begin to twist, and there'd be like a screw head on here that would also twist, and it would be very fine twisting. So what Cavendish did is he looked at how much that twisted, and by doing various measurements and looking how much that twisted, he was able to determine a value for the universal gravitational constant. So what Cavendish had figured out is he figured out the universal gravitational constant was about 6.74 times 10 to the minus 11 Newton meters squared per kilogram squared. Pretty good for 1798, considering he's only about 1% from the accepted value today. And as I mentioned, it's pretty amazing that he did that, considering this wasn't actually his objective in the experiment. He wanted to find the density of Earth, but in order to do that, he actually needed this value of big G. So Newton got the foundation for it. Cavendish sort of tied it up. Nowadays, if we're going to do something like with a torsion balance, we're going to finesse it a little bit. We're going to use like lasers and like computers and all that instead of like, giant lead balls and all that. But basically, this Cavendish experiment, Cavendish used the torsion balance in order to determine the universal gravitational constant. We'll talk about something similar in Physics 30 when we talk about Coulomb and his determination of the Coulomb's constant.